All right, let's move on now to talking about the backward Euler method for solving the one-dimensional consolidation problem. So in the forward Euler method, everything was formulated at the j-1 time step, which means we're using the previous time step to predict the future. In the backward Euler method, we use the end of the time step instead. So it's really easy. Instead of t of j-1, you just replace it with t sub j, right? Or you replace all the j-1 indices with a j in the d squared u dz squared term, the second derivative of u with respect to z. And the equation then becomes an implicit equation, which means that we can't develop an explicit equation for u of I comma j that can easily be solved based on parameters we already know. So let's go through that. Here's the equation that we end up with. CV is now at I comma j instead of I comma j-1. And then the terms in the second derivative equation are also all having j's. And then that's, again, equal to the du dt term, which doesn't change. Okay, du dt is still u of I comma j minus u of I comma j-1 over dt. All right, now we come down here, make our substitution for alpha for the c sub v dt over dz squared term after bringing dz over to this side. And then we simplify here, and we get this this equation where I've put all of the j terms on the left and all of the j-1 terms on the right. So we end up with a linear system of equations for the I comma j terms, I plus 1 comma j and I minus 1 comma j. Notice that this is an implicit equation because if we tried to isolate u of I comma j, we would have to bring these other I plus 1 comma j and I minus 1 comma j terms over to the right side of the equation, but we don't know those terms, so we can't solve for u of I comma j explicitly. So what we do instead is set up a system of equations using matrix algebra operations. So let's look here at the first, well, here's the first row. Let's look at the second row because that's the first fully formulated row in the system of equations. So basically what we have here is that I is equal, well, this one would be the I equals 0 row. This is the I equals 1 row, right? So we would have u, and then let's say that j is equal to 1 and then j minus 1 is 0. So we're looking at the very first time interval. Right, so the first row would be this minus alpha comes from right here, alpha times u of 0 comma j, right? So that's where it's multiplying right there. And then we have a 2 alpha plus 1 that's multiplying the u of I comma j, which again would be 1, 1, so it's here. And then we have another minus alpha for the I plus 1 comma j term, which is u2 comma j. Right, so this is an equation for the full system of equations here. And then we have a vector on the right side that's all of the j-1 components. So the solution is pretty simple, right? We've set up this equation right here. Notice that by using a constant alpha, we're assuming now that c sub v is a constant. All right, in reality, it might vary with depth and it might vary with time. And that's one of the benefits of using a numerical solution instead of an analytical solution. But for now, let's just say that alpha is a constant, c sub v is the same at all depths and at all times, just to formulate the equation. Got to do it one step at a time before you start adding complexity. All right, now within this system of equations, we do have two essential boundary conditions. As you'll recall, essential boundary conditions are ones that we impose directly on the solution before we do any sort of matrix inversion or anything like that. And those two essential boundary conditions are that we know that u of 0 comma j and u of n comma j must be 0 because we have double drain boundary conditions. So the way that we do that is to put in the known equation, the known values for u, run through the multiplication, and then we come up with a reduced order matrix, a reduced system of equations that we then solve for the other pore pressures. All right, this term is a 0, this term is a 0, and then this term is also 0, and that term is 0 too. So it turns out that all we have to do really is take the inside part of the matrix, right? Just leave out the top row and bottom row and the left column and rightmost column, and then solve that system of equations. So we condense it down. So let's say, for example, we have 100 nodes along our depth axis. Well, instead of having a 100 by 100 matrix, we would end up just with 98 by 98 because we've taken out, the essential boundary conditions. So now we have this matrix multiplication in terms of the unknown pore pressures, right? So these are not essential boundary conditions. These are what we're trying to solve for. And then we know all of the previous time step pore pressures. And of course, you can solve for uj just using a matrix operation. So uj is m inverse. M is this matrix times u of j minus 1, where uj and u of j minus 1 have to also be truncated, right? So instead of being 100 by 1, this would be 98 by 1, and this would be 98 by 1 too. We're taking out the known boundary conditions. All right, now this method is unconditionally numerically stable. Okay, when we did the forward Euler method, we had to be careful about selecting alpha to be less than a half. If alpha gets to be bigger than a half, you get garbage, right? The solution becomes numerically unstable and the answers don't make any physical sense. This one is unconditionally numerically stable. That means you're going to get physically meaningful results out every time. And the reason is it can be described here. Let's say that this black line corresponds to our solution path, right? So the actual real solution would follow that curved path. We're linearizing that path with the finite difference solution, so we're going to follow a linear path instead, and that linear path is going to be at the slope defined at the end of the increment rather than at the beginning, right? So for the forward Euler, we followed a path like this. Let me sketch it in there just so that we recall what was happening. And we would get a point way up here. So this one was forward. Okay, and then the backward Euler method, we're using the gradient at the end of the time step instead of at the beginning. So with forward Euler, if we have a concave down kind of solution path, we tend to overpredict, whereas with backward Euler, we tend to underpredict. Underpredicting means that the solution is going to end up being numerically stable. We don't have to worry about how big the time step is. It's always going to give us a solution. Now, that doesn't mean that that solution is perfect. It just means that you get a solution. You still need to worry about how big that time step is and how big your depth interval is. In general, the smaller we make those things, the more accurate the solution becomes. It just takes a little bit longer to solve it. All right, now you might be wondering, why would we go through the effort of forming this system of equations, and then at each time step we have to invert a matrix and multiply it by a vector, and that seems like a lot of work. Okay, well, it turns out that this backward Euler method can actually be much faster than the forward Euler method because we're not constrained by alpha, right? We can make alpha be much bigger than a half. So with the forward Euler method, your delta t might be so small that you have to do like thousands and thousands of calculations. And you don't really need to have delta t be that small. Maybe that's more resolution than you're really looking for, just to make a plot of settlement versus time or pore pressure versus depth at some time. Okay, with the backward Euler method, we can use much bigger time steps and still get a meaningful solution that's reasonably accurate. And so it can actually be much faster. Maybe instead of having to do 20,000 time steps, we can get away with only doing 100. So even though each step involves more calculating and this matrix inversion, the overall process can be end up being quite a bit faster.